Hi everyone, once again welcome back to our class. Now we are going to discuss about the acceleration due to gravity, some concepts based on the G, okay, and the kinematic equations of motions, freely falling body and the body projected upward direction. The equations of motions changes from one form to one equation to another equation. Okay, first of all, what is the acceleration due to gravity? Okay, here statement here, see, started acceleration due to gravity. What is the define the acceleration due to gravity? Now first this is defined easily simply. Here the uniform acceleration of a freely falling body towards center of the earth due to earth's gravitational force is called as here simply acceleration due to gravity. Once again, the uniform acceleration of the body, freely falling body towards center of the earth due to earth's gravitational field or earth's gravitational force is called as here simply acceleration due to gravity. So it is denoted by small g. It is denoted by here small g. Okay, the g value, small g value changes from one place to another place on the surface of the earth. The g values changes from one place to another place on the surface of the earth. The g values are constant at a given place. The small g values are constant at a given place, and the g values here, the body projected, for example, when a body projected upward direction, the velocity is decreases, but the acceleration due to gravity is negative. For example, the body freely falling downwards, the velocity is increases, but the acceleration due to gravity is taken as a positive. Generally, the g values changes from one place to another place on the surface of earth. Okay, the value of the g at the poles of the earth here 9.83 meter per second square, 9.83 meter per second square, as well as the acceleration due to gravity, the value of the acceleration due to gravity at the poles at the equators, the value of the g 9.78 meter per second square. Generally, the average value of the g on the earth here, that's value is 9.8 meter per second, 9.8 meter per second. Okay, in case of the value of the g on the moon, for example, on the moon, the value of the small g, okay, 1.67 meter per second square, that is equal to here acceleration due to gravity on the earth by 6. So g by 6 is equal to g nothing but here acceleration due to gravity on the surface of the earth by 6, that is equal to 1.67. This is our g values. In case the acceleration due to gravity on the earth sun, the value of g is equal to here 274 meter per second square, 274 meter per second square. These are the some information of the small g. Okay, first of all, statement here, note this one. Okay, the uniform, first of all, uniform acceleration of a body, the uniform acceleration of a freely falling body, freely falling towards center of the earth, okay, towards center of earth due to earth's gravitational force, earth's gravitational here gravitational force is known as simply acceleration due to gravity. Acceleration due to gravity. It is denoted by small g. It is denoted by here small g. Okay. Some finds ikkada konni finds raskondi. Its value is here. Its values of all bodies are constant. Okay, that means here constant. That means for a given place, constant at a given place. Okay, here next point, it is independent of, it is g values independent of size, shape, nature of the body and material of the body constitution. So some points here, it is independent of the shape, size, material and nature of the body. Okay, these points. Next point here, when a body projected upwards, the velocity increases. Next here, for example, this is earth one. For example, this is a earth. Okay, this one here earth. These are equator. For example, this one here pole. Okay, pole. Here north, south, east, west. East, west is a equators. For example, north, south is a poles. The g values at the poles. Okay, g values at the here poles. G is equal to here simply 9.83 meter per second. 9.83 meter per second square. Okay, and equators, and here equators g is equal to the value of the g at the equators. G is equal to here 9.78 meter per second square. 78 meter per second. So the average value of the small g on the earth 9.8. Okay, e points. So its value of g at the pole that g is equal to 9.83 meter per second. And next point, the value of g at the equator. Here g is equal to 9.78 meter per second square. 9.78 meters. So average value of the g on the earth. So next point here, average value of the g on the earth here. G is equal to 9.8 meter per second square. 9.8 meter per second square. Okay, these are very small information of the small g, acceleration due to gravity. Note this one. First of all, statement here, the uniform acceleration of a freely falling body towards center of the earth due to earth's gravitational force is known as simply acceleration due to gravity. It is denoted by small g. Next, its values of all bodies constant for at a given place. Next one, it is independent of the shape, size, material and nature of the body. Next point, the value of g at the poles 9.83 meter per second square. Okay, the value of the g at the equator 9.78. meter per second. Next, the average value of the G on the surface of the earth. Here G is equal to 9.8. Okay. Next point, note this, some few points here. The small g values on the moon. The small g values on the moon. Yeah, g values on the moon. Value of, next point here, value of g on the moon. On the moon here, g is equal to 1.67 meter per second square. That is equal to here, moon is equal to, so g earth by acceleration due to gravity on earth by 6. Okay. Next point here, the value of g on the sun. Okay. Here g is equal to 274 meter per second. Very important, this one here. G is equal to 274 meter per second square. So next point, when a body projected upward direction, so its velocity is decreases, but the acceleration is taken as here negative. The body projected upward direction, velocity is decreases, acceleration due to gravity taken as here negative. For a body freely falling downwards, the velocity is increases, the acceleration due to gravity taken as a positive. These are information of the small g. Okay, note this one first of all. Yeah, next, the equations of motion for a freely falling body. The equations of motion for freely falling body. What is the first of all freely falling body? The equation of here, 4 equations, kinematic equations, 4 equations here. S is equal to ut plus half it square, v is equal to u plus at, v square minus u square is equal to 2as, Sn is equal to u plus a into n minus 1 by 2. These 4 kinematic equations. Okay, these kinematic equations here changes from freely falling body. What is the first of all equation of motions of freely falling? What is the freely falling body? First of all, the motion of all the bodies, the motion of all the dropped bodies falling towards earth when the air resistance is ignored is known as simply freely falling body. Is known as here simply freely falling body. Once again, the motion of all the dropped bodies falling towards earth, center of the earth or earth, when the air resistance is ignored is known as here simply freely falling body. Okay, statement raskondi first of all. Here statement, motion of all the dropped bodies falling towards the earth, center of the earth. Okay, center of the earth, when an air resistance is ignored. Air resistance is ignored. Okay, ignored is known as a freely falling body. Okay, freely falling body. So the freely falling body, the body is dropped from the rest, some height from the height of the edge from surface of the earth. Here simply, for example, this is a surface, this one here surface. Okay, earth surface. The body at some height from the surface of the earth, some height, for example h height. The body point at a point, for example. Okay, this body dropped. Okay, this moving uniform acceleration, that is equal to g. downward direction, downward. So the acceleration due to gravity always acting downwards. The direction, always direction of the this body always is center of the earth, okay, always downward direction acceleration. So here the body is here drop. So initial velocity here, initial velocity is 0. The initial velocity here 0. H is the height of this body. This body to reach the surface with velocity here u, with velocity v. This body touches the ground with velocity v. Now the time taken to the body to reach the surface here t, okay, this is a t. Now t is time taken by the body to reach the earth surface. Here v means the touches the velocity of the body to touches the earth. H means height of the body. Here u means the initial velocity of the body. So a is the body placed at a point A. Okay. Now the kinematic equations. Note this one first of all. One second statement. The motion of all the dropped bodies falling towards center of the earth when an air resistance is ignored is known as simply freely falling body. Freely falling body. So in case of 4 cases here, 4 cases. Okay. First case v is equal to u plus at. Second one, very important formulas. Now here first one, first case here u is equal to 0 and here g is equal to g. Here a is equal to g. Okay, these values. Next, first equation here v is equal to u plus at. So here v is equal to 0. That means here simplifies here v is equal to at. So a is equal to just g. So a is equal to gt. This is a velocity is equal to gt. Velocity is equal to gt. So t is equal to v by g. T is equal to v by g. Next equation, second one here, s is equal to ut plus half at square. Now here s means h. S means here h. So h is equal to u nothing but 0 ut 0 plus 1 by 2 a is equal to g gt square. So simplies here h is equal to 1 by 2 gt square. 1 by 2 here gt square. Okay. Next one, third one here, v square is equal to u square is equal to 2as. Okay. Now final velocity, initial velocity 0 square is equal to 2 into a is equal to g. Here h is equal to just to h, for example here h. Displacement, this is a here displacement of the particle. Now v square is equal to simply 2g h. Here v is equal to under root of 2g h. This is a third equation. So this one simply v is equal to here 2as. Okay. Here also same, v is equal to 80. Next fourth one here, Sn is equal to u plus a into n minus 1 by 2. Sn is equal to u plus a into n minus 1 by 2. Now this is a u is equal to 0. Here u is equal to 0. Sn is equal to u is nothing but here 2 by a by 2 into here 2n minus 1. So here Sn is equal to simply a by 2 to n minus 1. So this one, the kinematic equations of motion freely falling body. This one first equation, this is a second one, this one here third one, this is a here fourth one. Now for example, the freely falling body, the distance of the body 1 second, 2 seconds, 3 seconds and 4 seconds, etc. So and so. So the ratio of displacements or distances in vertical direction, freely falling body, the ratios for a freely falling body, the distance traveled here 1 is to 4 is to 9 is to 9 is to 16 is to so on so. Okay, here simply some application చేద్దాం చూడండి. Note this one first of all. Note this here. The ratio for a freely falling body, distance covered by the ratio of distance covered. Simply note వేసుకోండి here. Note here. Simply this one, for example, surface. This body is some height, surface of the earth. Okay, first to second here, for example, here s1, here t is equal to just 1 second, t is equal to 1 second. Second, for example, this is a here displacement here s2, here t is equal to, for example, 2s. Okay, third second, for example, this one here displacement, this is a displacement here s3, here t is equal to third second s4, and so fourth second, for example, here displacement s4, here t is equal to just here 4 seconds. The distance, this one first seconds, this one, for example, second, this one here third second, this is a fourth second. Now this formulas, this values here, here Sn is equal to u plus here a into 2n minus 1. Okay, here formula here t is equal to 1, here u is equal to s2, u is equal to 0. That means here the body moving from rest position on the surface of the earth. Okay, now 1 second, so this displacement here s1 is equal to simply 0 a into here, this is a 2 1 minus 1. Okay, is equal to a into 2 plus 1. Okay, is equal to just a, just here ratio just a. Okay, s1 seconds. Okay, here this is a second, so here second case here yes s2 nothing but here a into 2 minus 1. Second, the distance traveled from a to this point, for example, a point, b point, c point, d point, so and so. Next, here t is equal to 2 seconds, t is equal to